Hello. So continuing with the topic on real numbers, which is the first topic in the O Level Maths syllabus, we're going to look at the subtopic of irrational numbers. So for this, irrational numbers, so part of that can be found in the New General Mathematics textbook, book 3, chapter 20. So numbers which can be expressed as exact fractions are called rational numbers. For example, 8, which is a whole number, 3 over 4, which is a fraction, 2.5, which is also a mixed fraction because we have a whole number and a fraction, and then square root of 16, because square root of 16 is the same as saying square root of 4 times 4, which is just going to be 4, or 0.3 recurring. So when you see this little dot on top of a number, it means it's recurring, which means it's repeated over and over again. So what that means is 0.33333 to an infinity number of times, and this can be translated to 1 over 3. So if you put 1 divided by 3 in your calculator, it will give you 0.33333 recurring an infinity number of times. And numbers which cannot be written as exact fractions are called irrational numbers. For example, 7 and pi, because square root of 7, and pi, because square root of 7, we cannot further simplify it to anything else. It just remains a square root of 7. It does not repeat itself, it just remains a square root of 7. When we try to put it in a calculator, it produces a number of different digits that are not repeating in a specific pattern or format. And pi, as we know it, is 3.14 and a number of other digits that follow. So for example, pi is if we were to write it further than 2 decimal places, is 3.14159265 359 and on and on and on. As you can see, there is no specific pattern that is being formed after the decimal place. So all recurring decimals, something to note, that all recurring decimals are rational numbers, is they can be expressed as exact fractions. So if something can be expressed as an exact fraction, for example, 3 over 4 here was an exact fraction. 2.5 can be 5 over 2, which is an exact fraction. So anything that is a recurring decimal, which means a decimal that has a repeated pattern after the comma, they're rational numbers, right? So looking into exactly what recurring decimals are and some examples. And part of the requirements is that one needs to know how to express recurring decimals as rational numbers, which means as exact fractions, right? So for example, this question says, express 3.17 with the recurring numbers or digits being 1 and 7 is a rational number. So like I mentioned before, 3.17, where 1 and 7 have the dots at the top, 3.17, 1 and 7. This means that 1 and 7 are being repeated in that order after the comma for an infinite amount of times. So that's going to be 3.17, 17, 17, 17, 17. It goes on and on and on. So if we look at it, we have 2 digits, right? 2 recurring digits after the comma. So since we have 2, this is going to be an indicator of what you have to do next. So how you can solve this is we want this to be a rational number, right? And the rational number means is an exact fraction. So we want to take it from decimal format to fraction format, and without using a calculator in this case. So what we have to do, so this is one of the methods of how you can solve this. There are different ways that can be used, but this is one of the approaches or methods that you can use. So you have two recurring digits. So you say, so let's see how we can solve this. So you say let n be 3.17 recurring. Again, we already know that this means 3.17, 17, 17, and on and on and on. Right? But because we have two digits that are recurring, as I mentioned, if we multiply 3.17 by 100, we move this decimal place 2 times, right? If we multiply it by 100, because we want the first digit of the recurring to be maintained is what we had when we had the number. So that's why we're multiplying by 100, because with two recurring decimal places, that means we multiply by 100. So it's you would multiply by 10 to the power of n, where n is the number of recurring digits. In this case, it's 10 to the power of 2, which is just 10 times 10, which is equal to 100. So in this case, we go back to our problem, and now we say what's going to be 100n, which is the same as saying 100 times n. So that's going to be 3,171717, your recurring amount of times 100. So multiplying this by 100 moves the comma or the decimal point 2 times to right there. This will be equal to 317, 17, 17, 17, a recurring amount of times. So now we have n and we have 100n, right? The next part is we say, what's 100n minus n? We subtract, right, to get rid of the n because they are on the same side of the equal sign. So we know what 100n is 317, 17, 17, 17, a recurring amount of times, minus 3, 17, 17, 17, a recurring amount of times. So whether you do this by the abacus method or any other way of subtraction, so these translate to 317, 1717 minus 3,171717, right? So since this repeats, all these are going to be zeros because they'll subtract each other. So you're going to get zeros to infinity. Then 7 minus 3, that is 4. And 1 minus 0, that's 1. 3 minus 0, that's 3. So now on the left hand side, we have 100 minus n, which is going to be 99n is equal to 314, right? That means n is equal to 314 over 99. If it was possible to simplify this further, I would simplify it, but there is no lowest common multiple that goes into both 99 and 314, because even 3 doesn't get into 314 without leaving a remainder. So then the answer is n is equal to 314 divided by 99. And if you put this in a calculator, you should be able to get 3.17 recurring. So that's how you solve that. So for example, we have another question which asks us to express 8.3 as a rational number. Again, we look at 8.3, knowing that when we take a look at this, 8.3 recurring, 3 is the one recurring, so that means 8.3333 an infinite amount of times is what the number is, but we only have one decimal place here, only one recurring number. So to move this to the other side of the decimal, we just multiply by 10. So we say let n be 8 3 recurring, and that means 10n is equal to 8.3333, an infinite amount of times 10, right? And this will give us 83.3333, an infinite amount of times. Then we do the same thing when now we say 10n minus n is equal to 83.333 minus 8.333, right? Which is, again, putting it in abacus format, 83.33 minus 8.333, on and on and on. And these become 0 after the comma, all these become zeros. And then 83 minus 8, that's going to be 5 and 7, right? 10n minus n, that's going to be 9n is equal to 75. So n is equal to 75 over 9. But 3 is a common multiple in both 75 and 9. So 3 into 9, that's 3. 3 into 7, that's 2, remainder 1. 3 into 15, that's 5. So n is equal to 25 over 3. But we know that n was 8.3. Recurring is equal to 25 over 3, which is an exact fraction. So if you put 25 divided by 3 in a calculator, you should be able to get 8.33333 recurring. So from the same textbook, which is the New General Mathematics, book 3, you can try the following examples. So first exercise is looking to determine which of the following are rational and which ones are irrational. So the question is asking which ones can be put in terms of exact fractions and which ones cannot be put in terms of exact fractions. So as an example, if we take r, which says root of 4.9, right? So sometimes that comes in a trick where you have to recognize what that is, because we have a decimal and a square root. So that would be the same as saying 49 divided by 10, right? That's the same thing. And when we do 49 divided by 10, that means as we are going to look more into the mathematical operations after this, we have square root of 49 divided by square root of 10, which translates to the same thing. And we know that square root of 49 is 7, because 7 times 7 is 49, which means it's going to be 7 over square root of 10. And we do not have square root of 10 simplified further. So then that already shows you that this is an irrational number. Because it cannot be expressed as an exact fraction. So it's one of those examples. And then the next one is saying express the following recurring decimals as rational numbers. So doing the same thing that we did in the examples that I gave you. So yeah, you can take a screenshot of these or pause to look at this and give those a try. And yeah, you can review what the answers are at some point. So at the same time, like I mentioned, for example, the example that I showed you here, where you're dealing with square roots, which also go into rational and irrational numbers, there are different mathematical operations that work around using square roots. So dealing with numbers under the square root, which are also called surds, when you're multiplying, for example, if you have square root of m times square root of n, is the same as putting both under the square root sign. So that becomes square root of m times n under the same square root, And then When you're dividing, for example, square root of m over n is the same as saying square root of m divided by square root of n, which is the same thing that I did here with square root of 49 divided by 10. Right, it's the same square root of 49 divided by square root of 10. So that's the thing that we do here with division. For example, if we had square root of 21 divided by square root of 7, that means square root of 21 over 7. So for multiplication and division, they can both go under the same square root of sign, under the same square root sign. So then that 7 into 21, that's 3. So that's how we get square root of 3. But when you now need to do other mathematical operation, you first have to factorize. For example, you can only add or subtract surds if they have the same base, if they have the same thing under the square root sign. So you have to factorize. So for example, if we have 35, right, we know that for under multiplication rules, 35 is the same as saying 7 times 5, putting it into its multiples, right? 28, that can be 4 times 7, but we know that once we do square root of 4 times 7, we can expand it further to say square root of 4 times square root of 7 under the multiplication rule. And square root of 4 is the same as saying 2 squared times square root of 7. And 2 squared means that we can remove the square root because it's 2 being repeated. That's what squared means. And then square root means to the power of half. So then we can remove the square root in that format. So then that just means the square root of something being squared is the square of that number. So that's going to be 2 square root of 7. Yes, because to remove the square root, if it's something that is a perfect square, it becomes the root of that number. So you can only, like I mentioned, you can only add or subtract if and only you can factorize to the same thing under the square root. You can't add square root of 5 plus square root of 7, right? You can only add if both of the square roots have the same number under. It has to be the same number under. So for example, here we have 3 square root of 5 plus 8 square root of 5. So by factorization, we factor out square root of 5, which means it's going to be 3 plus 8, which is 11. So that's 11 square root of 5. Or subtraction, 7 square root of 3 minus 4 square root of 3, which will be equal to 7 minus 4, after factoring out square root of 3, which we then get 3 square root of 3. And sometimes you need to factorize to get the same thing under the square root. For example, here we have 24 plus 3 square root of 6. So a question can come like this, and you have to recognize the thing, okay, how can I express 24 into something that can give me a perfect square? So looking into the different factors that give 24, so you either have 12 times 2, or you have 3 times 8, or you have 4 times 6, or you have 24 times 1. So looking into this, you then try to eliminate which ones don't work. So 24 and 1 would take us back to 24. 12 and 2, there is no perfect square. 12 is not a perfect square, 2 is not a perfect square. 3 and 8, none of them are perfect square. And 4 and 6 takes us close to what we have here, 6. And 4 is a perfect square, so we take 4 times 6. So 4 times 6 is the same as saying 24 plus 3 root 6, right? And then we have this. Now we can factor out this 4 because we know it's a perfect square. Taking out of the square root, it becomes 4 squared, which is 2 square root of 6 plus 3 square root of 6. So when we look at it, and now we have square root of 6 and square root of 6. Now we can add 3 and 2 once we factor out square root of 6, and then we get 5 square root of 6. So yeah, with more examples, for example, we have square root of 20. It's the same rules where you find two numbers that you multiply to get 20, preferably one of each, one of which has to be a perfect square. So looking at factors of 20, we know that it can be 4 and 5, where 4 is the perfect square, and factoring out 4 out of the square root sign, we get 2 square root of 5. Then the next question has square root of 45, and again we look at perfect squares. So perfect squares are like 4, 9, 16, 25, because that's 2 squared, 3 squared, 4 squared, 5 squared, and on and on and on. So 45 is 5 times 9, and 9 is a perfect square because that's 3 squared. Then we factor out 3, then we end up with 3 square root of 5. Again, it can come in a format of factors which are not really in numerical form, but we have x squared times y under the square root of sign. Again, x squared times y. X squared is a perfect square, so we take out x and we're left with y. So yeah, it then ends up becoming x times square root of y. So again, an example to try is under exercise 20c. Simplify the following by making the number under the square root sign as small as possible. So again, try questions 1, 3, 8, and 9 to simplify as simple as possible. And then exercise 20d under the same textbook to express them as a square root of a single number. So now doing the reverse of what you would have done on exercise 20c. So I can do number 5 as an example, where we have 5 square root of 2. That's the same as to put 5 back under the square root is the same as saying 5 squared now times 2, right? So that's how you put it, because to take it out of the square root, you find what number you would have multiplied twice to get a perfect square. So to put it back inside, you say, what do I get if I multiply it twice, right? And in this case, the perfect square of 5 squared, that's going to be 25 times 2. 25 times 2 under the rules of multiplication, that's square root of 50. So yes, so you can give these a snapshot and give them a try, and yeah.